let's talk about the most extreme material in the universe. And no, I'm not talking about black holes. The answer, believe it or not, is hiding inside every single atom that makes up, well, everything. So today we're going to dive into the absolutely mind-bending physics of the atomic nucleus.
Okay, just look at this number for a second. This is the density that physicists have calculated for the stuff packed into the core of an atom. That is 340 quadrillion kilograms crammed into a single cubic meter. It's a number so ridiculously big, it's basically meaningless without some kind of context.
All right, so here's your context. Imagine you could somehow scoop out a tiny piece of an atomic nucleus, just the size of a sugar cube. That single tiny cube would weigh more than every single human being on Earth put together. All 8 billion of us. Let that sink in for a minute. So right away, this brings up a huge question. I mean, we can't exactly put a nucleus on a scale or measure it with a tiny ruler. So how on earth do we know any of this? How do you measure something so small and so dense? Well, the answer is just incredibly clever. It turns out, to see something you can't see, you have to get creative. You have to build a kind of subatomic sonar. But instead of pinging it with sound waves, you blast it with a beam of super high-energy electrons. So what you're looking at here is the basic setup. You've got that beam of electrons on the left, and they're being fired at that super thin piece of foil in the middle. Now, as those electrons zip past the nuclei inside the foil, they get deflected. They get knocked off course. And that creates this beautiful wave-like pattern on the detector screen on the right. By analyzing that pattern, we can actually work backward and figure out the exact size of the thing that caused it.
Let's just walk through it. First, you rev up these electrons to insane energies, getting them tantalizingly close to the speed of light. Then, you shoot them at your target. The electrons spread out, creating that diffraction pattern, kind of like ripples in a pond. Scientists then just have to carefully measure the angle to the very first dark spot in that pattern, and using some pretty neat wave physics, boom, they can calculate the precise radius of the nucleus.
Now, here's the quantum weirdness that makes this whole thing possible. At these crazy high energies, electrons don't just act like little bullets, they also act like waves. I know it's strange, but at the quantum level, everything has this wave-particle duality. And the faster you make something go, the shorter its wavelength gets. The key is, to see something, the wavelength you're using has to be smaller than the object you're looking at. So by cranking the speed of the electrons way up, we're essentially tuning them into an ultra-high-resolution microscope, powerful enough to resolve something as tiny as a nucleus. And here's the really cool part. After doing this experiment with a whole bunch of different elements, from the lightest to the heaviest, physicists discovered something amazing. The radius of a nucleus, let's call it R, isn't random at all. It follows this beautifully simple formula, where A is just the total number of protons and neutrons inside. What this tells us is that all nuclei are basically built from the same stuff, packed together at the exact same constant density. And this is how we know that formula is absolutely spot on. When you plot the experimental data in just the right way, like you see on the left, you get a perfect straight line. This is the kind of thing that makes physicists jump for joy. It's a clear, undeniable signal that the relationship you found is real. Okay, so we've figured out how big the nucleus is, and we've confirmed this unbelievable density. Now let's talk about what's going on inside and how it leads us straight to one of the most famous equations in all of science. Right. We've all seen it, E=mc². But what does it actually mean? Well, at its core, it means that mass and energy are just two sides of the same coin. They're interchangeable. You can literally convert one into the other. Anytime something loses energy, it also loses a tiny, tiny amount of mass. And when it gains energy, it gains mass. Now, in our everyday world, this change is so small it's basically nothing. You know, a speeding car's mass increases by an amount so tiny we could never hope to measure it. But inside the nucleus, it is a completely different story. When a nucleus decays and spits out energy, the change in its mass, while still a tiny number, is actually a really significant chunk of its total mass. And that is where the power comes from. So to make this real, let's look at a very specific example. We're going to watch a nucleus of polonium-210 as it radioactively decays into lead-206 and an alpha particle. Okay, on this slide, we have the exact masses of all the players. Before the decay, we have the mass of that one polonium nucleus. And afterwards, we have the combined mass of the brand new lead nucleus and the alpha particle that got shot out. But hang on a second. If you actually add up the after masses, you'll see they don't equal the before mass. Something's missing. Physicists have a name for this. They call it the mass defect. The difference, that missing mass, is exactly 0.00581 atomic mass units. It's like a tiny little scrap of mass has just vanished into thin air.
But of course, it hasn't vanished. This is it. This is E equals mc squared in action. That missing mass has been converted into pure, raw energy.
And when you run the numbers, that tiny bit of lost mass unleashes 5.41 million electron volts of energy. Now, that unit probably doesn't mean much to you, but to put it into perspective, the energy from this single atomic decay is millions of times more powerful than the energy from a typical chemical reaction, like burning something. This is the awesome power locked inside the nucleus. So all of this leads us to one final and maybe the most fascinating question of all. You have all this energy, and you have all these positively charged protons crammed together that should be repelling each other like crazy. So, what is holding it all together?
No, seriously, think about it. The force pushing those protons apart at that close range is enormous. By all accounts, the nucleus should be the most unstable thing in the entire universe. It should instantly tear itself to pieces. And yet, here it is, the stable foundation of you, me, and everything we see. How is that possible?
The answer is a totally different force of nature. As you can see here, there is a kind of cosmic superglue holding those protons and neutrons together, an attraction so powerful it completely overwhelms their urge to fly apart. This is the strong nuclear force.
And this force has some very specific, very weird roles. For starters, it is by far the most powerful of the four fundamental forces. But, and this is a big but, it only works over incredibly short distances, basically the width of a nucleus. It's also an equal opportunity force. It grabs onto protons and neutrons with the exact same strength. And what's really wild is that if you try to squish them too close together, the force flips and becomes repulsive, which stops the nucleus from collapsing in on itself. This binding energy from this strong force is the mass defect. It's the energy that gets released when that missing mass is converted. So in the end, it's this incredible balancing act, an unbelievably powerful force holding together matter of unimaginable density, and in the process, turning a part of its own mass into the energy that binds it all together. It's the force that builds our entire world. Which leaves us with one final, very powerful thought. If this force is strong enough to hold the universe together, what kind of power do we unleash when we figure out how to break it apart?